Okay, so using this with all your x prime and x double primes equal to 0 when x equals 0, and you didn't really need x double prime equals 0. Never used it, so it wasn't a necessary assumption. And making the correction that I forgot to put the x on here, so that changes things a little bit, but your equation becomes this, and that's very straightforward. So now we solve for the Laplace transform. Well, it appears that if we factor out the L of x of t here, we get something very much like a characteristic equation. So that Laplace transform of x of t equals this, right? Okay, so this means that if we know the values of A, B, and C here, we have, well, it's what's called a system transfer function, okay? Okay, if you know the values of A, B, and C in the function f of t, then you get the Laplace transform of your x function, and you can inverse transform it. Now we're going to work a little more with doing inverse transforms today with the, integration by parts and stuff, and identifying our functions and matching them up, because we haven't done a whole lot with that, but you understand that if we know the Laplace transform of x, we can then use usually partial fractions to figure out what x is, okay? Now, that's one thing. Okay, so if we know A, B, and C, that's easy to, and can Laplace transform our f of t function, that makes it easy. And there's a whole wide variety of functions we can do. We can do step functions, we can do any power function, any trigonometric function, okay? Any exponential function, and pretty much any product of functions of that nature. Because it's just basic integration by parts in most cases, or substitution. Okay, well, okay, so this is what we have. We're going to call this the system transfer function. Let's say now that somehow that we've observed, well, we know what our function is here, and we've made observations, so we know what x of t is. Okay? So if we know this Laplace transform, and if we know this function, and we can calculate the Laplace transforms, then we should be able to get this function. That makes sense? And if we get this function, then we know what A, B, and C are. Okay? So by observing what the function, or what the system does in response to a driving function, we can figure out what A, B, and C are. Okay? So we can figure out what the differential equation was. Now, that might not totally make sense until you actually get your hands on it and do it, but it means, for example, for a circuit, you don't know exactly what's in the circuit, but you drive it with some voltage. That would be the f of t function, okay? And you observe how it behaves, and you figure out what this function is, and then you know what your circuit was. Okay, or at least you know what an equivalent circuit would be. Or you have a simple harmonic oscillator, and you just have it sitting there. Okay, no voltage, no force on it, and no displacement and everything. In other words, x and x prime are 0. It's at equilibrium. It's not moving. Okay? Then you apply some force to it for some time. Okay, maybe you accelerate it or apply a constant force to it in this direction. Well, the net force is that constant force minus kx, okay? And maybe you don't know what k is, and maybe all you do is observe the motion of the system, okay? So you observe this, and you know what this is. Then you can figure out A, B, and C, which tells you, again, what's going on with this thing, okay? And it would work for a simple harmonic oscillator where you've got a drag force. And that would be your Bx prime, okay? So it's very profound. Just thinking in terms of those two examples, both of which you're familiar with, especially right now because you're familiar with the circuits, or you're getting more and more familiar, you know what I'm talking about here, okay? You know how you would measure your input function, and you know how you would measure the current function, okay? Or charge function, or whatever. And you know how you'd hook the thing up, so you can relate to that, okay? And then for a pendulum, say in water, okay, just imagine, okay, I'm going to give this pendulum a push, and I'm going to measure the push. So I know my force function. And then I'm going to measure its motion, you know, the motion detector or whatever, okay? And from those two functions, I can figure out what A, B, and C are, and those have an interpretation, right? Okay? A's your restoring force constant, okay? B's your drag constant, okay? And C just has to do with your equilibrium position, okay?